systematically coming up with ways to integrate functions that are not necessarily easy to integrate. And one idea is called substitution rule, and the other idea is called integration by parts. And they both correspond to differentiation formulas, actually. So our anti-differentiation formulas don't really tell us anything about this one. But let's say you looked at doing a substitution. Let's say you had u equal 1 plus x squared, and du, being a differential that should work like a derivative, should be 2x dx, right? Because if you were to divide, if you considered what du dx is, that's a derivative, right? So that must be 2x. And then if you multiply by the differential dx, you can reasonably conclude that du is du dx times dx, which is, in this case, 2x dx. So, in this case, now we can convert this into a formula of the form. So note that we can put this over here with the dx, and you can have a square root of u du, right? So, therefore, you can do the integration. The square root of u is u to the 1/2. So you divide by a 3/2, thereby giving you 2/3 u to 3/2 plus c. And voila, you got it. Well, you can go and double check that using the chain rule. And using the chain rule, 3/2 will come out, multiply out by the 2/3, and taking the derivative of x squared plus 1 will come out and give you 2x. And what do you know? You get back the same thing as before. So it checks out. So take a look at this. If you had an integral of f of g of x times g prime of x, you could simply do the substitution u equals g of x, and then you'd note that du should equal du dx or g prime of x dx. And therefore, this all transforms into simply the integral of f of u du. So that's very interesting because what we have here really almost corresponds with what taking the derivative of f would be, except there's no prime in the set. So it's pretty much almost the inverse of the chain rule. So that's very cool. Okay. But not exactly the inverse of the chain rule, but very closely, almost that. And so over here now, let's say we have x cubed times cosine of x to the 4th plus 2 dx. Let me just good about that. We'll find it advantageous to have our u be x to the 4th plus 2. So du should equal dx, dx, my mistake. That should equal, that should be equal to a du dx, and du dx is 4x cubed, and then dx. So now this integral will transform into now the integral of And note that x cubed dx will equal 1/4 du. So now we'll get 1/4 cosine of u du, which has the antiderivative of 1/4 sine of u plus some arbitrary constant. And then you can substitute back in, right, 1/4, not cosine, sine of x to the 4th plus 2, all plus some arbitrary constant. Alright, so of course the main challenge is always to come up with an appropriate substitution that's worth your while. Okay? So let's take a look at this one. We could have, in this case, u equal 2x plus 1. So note that du will equal 2 dx. So we should solve for dx to be 1/2 du. And now the integral transforms into the square root of u times 1/2 du. So we can write this as 1/2 integral u to the 1/2 du. We then integrate that, so we get 1/2 times a 2/3 u to the 3/2 plus some arbitrary constant. 1/2 will cancel out the 2 and the 2/3, and then we can substitute back in and write this as 1/3 times 2x plus 1 to 3/2 plus some arbitrary constant. Okay. And now another substitution is just let u be what you had, square root of 2x plus 1. Now, you differentiate and find the differential transformation in this manner. You find du is going to be dx over square root of 2x plus 1. So dx is the square root of 2x plus 1 du, but we know that's also u. So dx is u du. Okay, so therefore, well, that's u, and this is u du. So you get the integral of u squared du, which integrates out to be u cubed over 3 plus c, and then you substitute in the square root as 2x plus 1 to the 1/2 power. And now you have the same thing as we had before, 1/3 of 2x plus 1 to 3/2 plus an arbitrary constant. Okay, let's have some fun with this one. All right. So in this case, I think it will be most advantageous to have well, we have several options here. Let's say, for example, we had u equal 1 minus I'm sorry. Yeah, 1 minus 4 x squared. So du will equal negative 8x dx. So x dx is negative, it's negative 1/8 du. So this integral will now transform into a negative 1/8 integral of u to the negative 1/2 du. We integrate that, we're going to get a negative 1/4 u to the 1/2 du, which will, I'm sorry, why did I write that? Du. Plus an arbitrary constant, which is, or if you substitute back in a negative 1/4, square root of 1 minus 4 x squared plus some arbitrary constant. All right, well, this is actually an easy one. You just have u equal 5x, so du equals 5 dx, and therefore dx is 1/5 du, and so now we get 1/5 integral e to the u du, which is of course 1/5 e to the u plus an arbitrary constant, or if you like 1/5 e to the 5x plus some arbitrary constant. All right, the tangent. Well, if you want to find that one, you want to have the tangent written as the sine over the cosine. So we should write this as the integral of sine of x over cosine of x dx. In this case, we'll find it advantageous to have u equal cosine of x. So du, therefore, will be negative sine of x dx. So therefore, sine of x dx is equal to negative du. So the integral now transforms into a negative integral of du over u, which is now the negative natural logarithm of the absolute value of u plus some arbitrary constant. And so if you like, that's negative natural logarithm of the absolute value of cosine of x plus an arbitrary constant. Some people don't like the negative sign, so they use the power property of logarithms and write this as the inverse of the cosine, which is the same thing as the secant. So you can rewrite this as an actual logarithm of the absolute value of the secant of x plus some arbitrary constant. Okay? So far, so good? Okay, great. All right. Now, if you want to apply all this to definite integrals, well, one way is you simply find the antiderivative based on what you did, and then finally plug in the endpoints and take the difference. Well, you had to take time evaluating the indefinite integral before you do it. But what if you do it all at once without substituting back in for what u is? What if you could transform the endpoints? The endpoints, in fact, should transform according to what your substitution is, right? Well, let's double check this. So in this case, let's say we made indeed the substitution that let's say we did substitution u equal the square root of 2x plus 1. As we already learned before, if we do that du, you get dx over the square root of dx 2x plus 1, thereby giving you that dx is u du. And so our integral square root of 2x plus 1 dx therefore transforms into the integral u squared du. Now, but what about the endpoints? So the endpoints should transform according to the transformation. So if we have a 0 and a 4 here, let me figure out where to write it. Let's say that the 0, that should transform now into now being a square root of 2 times 0 plus 1, which is 1. And the 4 should transform into being a square root of 2 times 4 plus 1, which is square root of 9, or 3. So that should transform into the integration from 1 to 3 of u squared. So you get 1/3 u cubed evaluated from 1 to 3. So you get 27 minus 1 all over 3, which is indeed 26 over 3, as expected. Checks out. Right? So it works. That's fantastic. All right. So we can do that. No problem. Okay. Just transform the limits of integration according to substitution. That's it. And here's the geometric interpretation. So the if you go ahead and were to do, let's say you did other transformation, we had u be 2x plus 1. Well, then it gets moved over 1 and it gets stretched out. And so actually, if you just calculated this area, it wouldn't be the proper area. So you have to take that into account. You have to take that into account. All right. So the differential will introduce a additional factor of 2. All right. Okay. Over here again, we can well, there's no point in including negative signs, so I'll just integral from 1 to 2 of dx over 5x minus 3 squared. I will use u substitution. U equals 5x minus 3. So du equals 5 dx, and dx equals 1/5 du. So now we get the 1/5, the integral, and well, 1, of course, we'll note 1 is going to transform into a 5 minus the 3 is 2, and 2 will transform into a 5 times 2 minus 3, which is a 7. So we're going to be going from 2 to 7 of du over u squared. And we go ahead and integrate that. Now we have 1/5 times a negative 1 over u, going from 2 to 7. So it's going to be 1/5 of a negative 1/7 plus a 1/2. So if I combine that all into one fraction, I'll have a 1/5 of minus 2 plus a 7 all over 14. And it just so happens negative 2 plus 7 is 5, so we get 1 over 14, as expected. All right, that is a rather cool one. This is one I'm going to do 2 different ways. You'll see the other way later. to have our u be an actual logarithm of x. So our du, in fact, will be simply the dx over x. That's one possibility we could do. So if we do that, now we'll have the integral of u du. And 1 will transform into an actual logarithm of 1, which is 0. And e will transform into an actual logarithm of e, which is 1. So we go from 0 to 1. And that will, of course, calculate out to be 1/2. Okay. Symmetry. We like to take advantage of symmetry sometimes. So let's say, as you recall, an even function is where the f of negative x is f of x. And an odd function is where you have f of negative x introduce a negative sign and corresponds to being negative of f of x. So for example, x cubed is an odd function, whereas x squared is an even function. So it turns out that if it's an even, you have the exact same amount of area on the other side of the y-axis, thereby only making the integration from 0 to a necessary, and then you can just multiply by 2. But for an odd function, if you're integrating from negative a to a, you have a net area of 0 because you have an equal amount of negative area to an equal amount of positive area. So here's a nice illustration of that. Even and odd. One gives you twice what you could get going from 0 to a. The other one gives you nothing. What do you prefer? So we could go ahead and note right here for this peculiar function, it almost looks even. But no, only the denominator is even. The tangent of negative x is always the negative tangent of x. So therefore, it's an odd function. And therefore, if you integrate it from negative 1 to 1, despite the fact we probably would have had a great deal of difficulty being able to solve it, if at all, for the general antiderivative, we know this given definite integral must be 0. All right, last but not least, integration by parts. So I'll try to finish this before class is over. It's a lot to go over in one day, I know. All right, so as we know, every differentiation rule has a corresponding integration rule. The substitution rule, as I said, kind of corresponds to being a chain rule for differentiation. Now, we happen to have an integration rule that corresponds to the product rule. So if you were to take the derivative of f of x, g of x, you get f g prime plus g f prime. So it must be true that if you integrate both sides of this equation, the integral of f g prime plus g f prime is f of x g of x. So what if we were to subtract one of these onto the other side, and thereby get our formula for integration by parts? You have to choose your g prime and your f, and then integrate the g, multiply by 2, take the derivative of f, and multiply by g. And hopefully, if all goes well, this will be an easier integral to solve. If all goes well. Maybe not. So we like to use this UV notation. So we have u be f of x and v be g of x. So then du is f prime dx and dv is f, I'm sorry, du is f prime dx and dv is not f prime, but it is a, actually I don't need an eraser. Yeah, so dv is, of course, going to be g prime of x dx. So that way you can write it as integral u dv equal to uv minus integral v du. Okay? So let's take a look at this one. Now actually we want to get rid of this x factor, right? So we want to take the derivative of x to get rid of it. So we want our, so u dv, so we want our x to be our u. So u should be x, and our dv should be our sine of x dx. So that means that du is dx, and if you undifferentiate v, then v should be negative cosine of x. And we could add a constant, but why make things more difficult? Okay. So this, of course, must be uv minus the integral of v du. So we end up getting negative x cosine of x minus the integral of a negative cosine of x dx. Of course, that's negative and negative is positive, so we get a negative x cosine of x plus the integral of, I'm sorry, getting ahead of myself, and then plus the integral of the cosine of x. And the integral of the cosine of x is none other than the sine, so you get negative x cosine x plus sine of x, and then we should add in an arbitrary constant. No problem, right? But what if you were very foolish, or you decide you want to see what happens if you do it the other way around? Then you don't make an easier problem, you make a more difficult problem. Because if you have u be sine of x, okay, so if you did that, let's say you had u was the sine of x, and you wanted your dv to now be x dx, then your du will be cosine of x, and your v in simplest form will be 1/2 x squared. So your uv will be x squared over 2 times sine of x, and your v du now will be a 1/2 x squared cosine of x dx. This is a more difficult integral to solve. So don't do that to yourself. Choose a u and a v that makes a simpler problem, not a more difficult problem. So that's why you have to be careful about what you choose to be your u and what you choose to be your v. So choose it such that you get an easier problem and not a more difficult problem. So let's take a look at this one. This problem looks deceptively difficult, but in fact is easy, believe it or not. So I'll show you how easy it is. Simply, let's have u be natural logarithm of x. well, what's dv going to be? dv has no choice but to be dx, right? And if you take the derivative of u, or its differential, you get 1 over x dx. And the simplest form for v is x. So, of course, we should be looking at uv minus the integral of v du. Well, our v is x, our u is natural logarithm of x, that's x natural logarithm of x minus, okay, v was x, du was 1 over x dx, so so that is x natural logarithm of x minus, in simplest form, integral of dx. Well, we get x natural logarithm of x minus x plus some arbitrary constant. As simple as that. Okay. Now, in this case, it's not going to be enough to do integration by parts one time. We have to do it 2 times. So, for starters, let's have u be e of t, since e of t never changes anyways. And, no, sorry. We want to do it the other way around. So we'll have u be a t squared. That way when we take the derivative, we reduce the power of t. And then we want dv to be e to the t dt. So now our corresponding du will be 2t, and our corresponding v in simplest form will be none other than e to the t. So now we get so our uv, of course, is going to be a t squared e to the t, and then minus our integral of v du. Well, we have e to the t times a, now, excuse me, it should be a dt there, times a 2t dt. So now we have another problem. We want to find the integral of t e to t dt. In this case, again, we'd like u to, well, not, yeah, we'd like u to be t and dv to be e to t dt. Our corresponding du will be dt, and our corresponding v in simplest form is again e to the t. So this means our uv is simply t e to the t minus the integral well, v du, so v was e to t dt, and so therefore we get t e to the t minus e to the t plus some arbitrary constant. But so now we just need to multiply this by -2 and add it to t squared e to t for the general formula, and so we get t squared e to the t minus 2t e to the t plus 2 e to the t and then plus some arbitrary constant. And if you like, we can rewrite this as a t squared minus 2t plus 2 all times e to t plus some arbitrary constant. And that's the simplest you can make it look. Okay? All right. So, of course, if you want to do it for a definite integral, then you just have to make a definite integral. So, the uv, or in this case fg, you then have to evaluate between a and b and take your difference. So that's the only complication to that. So let's look at this integral from 0 to 1 of the arctangent of x. Well, in this case, they simply had u be the inverse tangent of x, and our dv be our dx, with the corresponding du being dx over 1 plus x squared, and v being in simplest form x. So of course, if you evaluate this x arctangent of x between 1 and 0, at 0 it's nothing, and at 1 you end up getting a pi over 4. This other part you can evaluate through substitution, the x over 1 plus x squared. Just note that the integral from 0 to 1 of x over 1 plus x squared dx, so let's say you have a u equal a 1 plus x squared, du will be 2x dx, so x dx equals 1/2 du. So now the 0 will transform to a 1, the 1 transforms to a 2, and you get 1/2 times a 1 over u du, which will turn into 1/2 natural logarithm of 2 minus 1/2 natural logarithm of 1, which is just 1/2 natural logarithm of 2. So in this case, we had to use both methods. So we get pi over 4 minus 1/2 natural logarithm of 2. All right, this I believe is the last example. So you have to actually use integration by parts and then algebraically solve for what you want to find. And I'll show you what happens. So actually, before I do this one, let me do something that's a little simpler, so you get the idea of what I'm talking about. Let's go back to the example of natural logarithm of x over x. Let's say I were to do it by parts instead. So I could have dx. I could have u equal natural logarithm of x, and I could have dv equal dx over x. The corresponding du then will be 1 over x, and corresponding v will be none other than natural logarithm of x. So what happens when you do it this way now? Well, you'll have your uv minus, of course, integral v du. Your uv will be the natural logarithm of x squared. And then you'll have minus the integral of v du. V is natural logarithm of x, and du is, I'm sorry, there should be dx there, will be now a dx over x. But look, take a look at this. This is exactly what you started off with. But what if we just add this to the other side and divide by 2? Right? So in other words, we have, if we let I be our integral, natural logarithm of x over x dx. Now this turns into an algebraic equation. I equals natural logarithm of x squared minus I. So if you solve that algebraic equation, you get I equals 1/2 the square of the natural logarithm of x. Fair enough? Okay. So, and of course, actually, in that case, you should add in an arbitrary constant, but whatever. So it's the same idea here. We're going to have to ultimately do an algebraic manipulation after using the integration by parts. So in this case, we would like our u to be a sine of x, or no. Yeah, we'd like our u to be a sine to the n minus 1 of x, and our dv to be a sine of x dx. Okay? So if you were to differentiate du, u to get du, you'll get a n minus 1 times the sine of n minus 2 of x dx. And the antiderivative of, well, dv, or the the simplest form for v is going to be a negative cosine of x. So let's note that our v du now will have a I'm sorry, I forgot to multiply by cosine. Yeah, due to chain rule, we'll also get an additional cosine in a du, cosine of x dx. So let me go ahead and write this out over here. So v du now consequently will be a minus a n minus 1 times a sine to the n minus 2 of x cosine squared of x dx. Note, cosine squared of x equals a 1 minus the sine squared of x. So we can go ahead and substitute in 1 minus sine squared into the cosine squared, and this will become a n minus 1, or let's see, yeah, n minus 1 sine to the n of x and let's see, and then minus a n minus 1 times sine of n minus 2 of x. And then all that being times the dx. Alright, so let me kind of bracket that in. Okay, this sine to the n actually corresponds to the original thing you're trying to find. So consequently, this is going to transform into the algebraic equation of I equals the negative cosine of x sine to the n minus 1 of x. That's your uv right here. And now plus, let's see, yeah, I'm sorry, so obviously we're subtracting, so this is v du, but we're actually subtracting v du, so this is going to get reversed. So now we'll have a plus the integral of, and I'll take the n minus 1 on the outside, sorry, plus n minus, not plus, minus 1 integral of sine to the n minus 2 of x dx. And now, because that's being subtracted, it's become a plus, and that's, I'm sorry, so that's n minus 1 times sine, I'm sorry, yeah, right here. So we have n minus 1 times sine to the n. So when that's being integrated, that will be equivalent to n minus 1 times the original integral. So we'll have a minus n minus 1 times our original integral. So if we add this to over here, we'll end up getting ni equal to this. And then we can just divide by n and get that. So that's how you do it. And I think we can call it a day. All right.